Well, hello. It looks like someone's drawn my sign convention wrong, and I'll have to fix that so we can not be all topsy-turvy like this. But right now, what I want to do is work an example problem for you on forces, net forces, equilibrium that we've begun talking about in this chapter 22 unit. So here's an example for you. What is the acceleration of a 500-gram plate sliding on a table with a static friction coefficient of mu equals 0.4 when a force of 3 newtons is applied horizontally? Wow, that's a lot, but it's not really a lot. It's a pretty simple problem, and we just have to get started on it and figure it out. So what do we do first? Well, we always draw a drawing, and we're calling them a free body diagram now that we're analyzing forces. And as usual, my drawings are just rather simplistic. Probably too simplistic at that point. Okay. Draw something resembling a plate. Okay, like a dinner plate. Okay. And this is the plate. And we're going to assume our sign convention up and to the right is positive. And then we're going to start filling out what we know about this plate, okay? The plate has some acceleration, okay? It has some mass. There's friction involved. There's applied force. So let's start talking about those things. So let's look at this plate. It has some mass, so it's going to have some weight, isn't it? Okay? And if it has weight and it's sitting on a table, the table has to push back against it using the normal force, or it would just plow through the table. So we're going to assume movement in the right-hand direction in a positive way. And we're going to get that by applying a force. Force applied. Okay? Well, what resists that force applied? The force of friction. Okay? And we're going to call that F sub mu. Okay? That pretty much tells us that that's a friction force. Okay, so of course now we have to start saying this over here so everyone's clear about what thing we're talking about. Friction, okay, normal, applied. That's pretty straightforward. We should go ahead and put it on there, okay? M is mass. Okay. What else do we need? Oh, we need G for gravity, don't we? And we're going to go ahead and say that that is 9.8 meters per second squared, so we understand that, right? And we'll put mass in kilograms, just so we know that we're talking about kilograms. Okay. And the last thing, since we have this N in here, we want to make sure that when we're using N, we're talking about normal. So we want to put NT for newtons. Okay. NT for newtons. And that should do us. Okay. As always, you can just wait to box it in or not box it in at all, but I like to kind of box mine in and keep it over there. It draws the reader's eye to that so they can decipher what's going on. Okay. So what do we know so far about this problem? We know there's an acceleration. We know there's some friction. Okay. So it's moving in the horizontal direction. It can't move vertically because the weight and the normal force oppose each other. So we have to kind of figure that out and then figure out which way it's moving. So what we're really looking for in the end is the acceleration is equal to the net force divided by the mass. And we know the mass, okay, but we don't know the acceleration and we don't know the net force yet, do we? Okay, so that net force, we're going to say it's horizontal. Okay, remember we don't really have all the tools yet to do things combine horizontal and vertical, and we always look at those two things separately when we're doing these types of problems. Okay, so vertically, there's no movement. Okay, no movement, no acceleration. So the net force vertically is 0. Okay, and later on courses, you'll always see a symbol, the sum, okay, of the forces in the y direction, okay, or the forces in the y direction, sorry, is equal to 0 is usually how they say that, to say no movement, okay? But we can just go ahead and say the weight force, which is acting down, opposes the normal force, so the normal force minus the weight force is equal to 0, okay? So the normal force is equal to the weight. What is the weight? Weight is the mass times gravity, okay? And that's 500 grams, or 0.5 kilograms, times 9.8 meters per second squared. And then we should go ahead and put a conversion in here and say 1 Newton is 8 kilogram meter per second squared. And then you'll notice that all of our units will divide out nicely, kilograms with kilograms, meters with meters, second squared with second squared, and we're going to come out with our normal force in kilograms, which is what we want. That is a weight, and the forces are in newtons, okay? So there we have the normal force, okay? And once we know the normal force, then we can start figuring out what this friction force is. Remember we said in class, okay, that the friction force is equal to the mu times the normal force. Okay? So that's pretty easy. We say 0.4, okay, times this up here, and that actually calculated out to be 4.9 newtons, okay, times 4.9 newtons. Remember, the friction coefficient is unitless, and that's going to give us 1.96 newtons, okay? So now we know the friction force, okay? We know the applied force, okay? 3 newtons, okay? And we can find the net force in the horizontal, okay? Horizontal. Is not equal to 0, right? So we have the applied force minus the friction force, okay? And what's that going to be equal to? That's equal to mass times acceleration, remember? Okay, up there. Okay. So to solve for acceleration, just going to say applied force minus the friction force divided by the mass. The applied force is 3 newtons minus 1.96 newtons, and all of that is divided by 0.5 kilograms. And then we should say 1 Newton is equal to a kilogram meter per second squared. Well, look, we can see that our newtons will divide out, our kilograms will divide out, and we're left with what? Meters per second squared. That's an acceleration. Okay? So when we work that out, the acceleration is going to be 0.52 meters per second squared. And we'll box that in, draw our reader or grader its eyes right to where we want it to be, and we've solved that problem. And I'll zoom out and give you a whole picture of this, okay? Hopefully you should be able to read that better.